So with that, I think we are all ready to get started. We have enough people in the room here and as well as on Zoom. And I see Christopher there. Hi, Christopher. So do you want to take it away from here? The board is all yours.
And welcome everyone. Let's see how things go today. So let me start sharing my screen. And up here I have a reminder of what we spoke about last time, which are the three main challenges in data analysis, at least the way I formalize them for LIGO, Virgo, Cagra gravitational wave data analysis. We have the first question, the detection problem of, is there a signal in the data? Having established that there might be a signal in the data, we then can have the parameter estimation challenge of, okay, what are the source properties of this signal? And we know that for compact binary coalescences, we have good models for the waveforms, so we can match those to the data and infer the source parameters. So that's great. That gives us our first astrophysical insights. However, we want to go beyond that. We want to not just look at one event at a time, but look at the entire population. So do population inference and infer the underlying astrophysical distribution of sources for our ensemble of observations. Now, each one of these challenges has a lot of theory behind it, a lot of development of algorithms over the years, and we could quite happily spend an entire lecture course speaking about each one of these. However, in this lecture course, we're going to focus on this final one, the population inference challenge, because this is the one that is most intimately connected to understanding astrophysics of the source. This is how we can best measure the many uncertain properties of the formation of compact binary coalescences. And I think also because this is the one which is under most active development. We needed to solve the detection challenge first to find any signals. Having found signals, we then realized, okay, we need to understand the sources. And now starting to amass a large number of observations, and that will only grow with time. We're realizing, okay, now we need to understand how to use this population. So I think population inference is perhaps the least well-known of these challenges and the least understood. So we're going to talk about this a bit more today. Okay, so as before, please do put your hand up or ask a question in the chat if you have any questions. And we'll go through and start discussing some population inference related matters. So just as a reminder, we have a whole host of different formation channels suggested for forming merging binary black holes, binary neutron star black holes. So we have primordial black holes, then we have a range of different astrophysical black holes. We have ones with binaries forming what we say is in isolation, but we realize is not actually properly in isolation because there still can be dynamical interactions in young stellar clusters. Then we have the dominantly dynamical formation of nuclear star clusters, globular clusters where we have many interactions. We also have potentially AGN disks playing a big role of these. And each one of these channels should produce a different distribution of masses, spin magnitudes, orientations, redshift evolution, eccentricity. So if we measure these distributions, we'll understand something about the physics that goes into these channels. And each one of these predictions has a whole host of different uncertainties associated with it. Okay, I'm told my video is freezing again. As long as you can hear me and see the screen, I think that's okay. Are you able to do that? Yeah, cool. Okay. Do let me know if I drop out at any point. And I'll do my best to try and catch up with it. Okay, where were we? Yes. So we have a whole host of uncertain physics in these that will also impact these distributions. So we really want to know what these distributions are. Now, we can do this in a number of different ways, but the way I'm going to focus on today is the way that's mostly employed by the LIGO-Virgo-Cagra collaboration. And that is by saying, what if we have some kind of phenomenological model, some parametric model to say the mass distribution, a power law, say, that we're measuring the slope of, a Gaussian that we are fitting the mean standard deviation to. Let's fit these to our observations and let's infer the properties of these. So we have an inference task. How do we tackle this? Well, we spoke a little bit about inference last time when we were discussing the parameter estimation problem, when we were talking about how do we measure the properties of an individual source given the data. And we spoke through how we apply Bayes' theorem in this particular case. So we have the data in D, and we're interested in inferring theta. This stands for the set of parameters describing the source, the masses, spins, distance, inclination, and so on and so on. So we want, what is the probability of these parameters given the data? We have the data, we know what's going on. And so we're going to end up with a probability distribution, and this is what goes into making our nice plots. So we have, say, a probability distribution, M1 versus M2. We've seen a few of these. We have, by convention, M1 is greater than M2, and we'll have some probability contour, say, that says, okay, there's a 90% probability that we're inside this contour. Okay. And I guess we could also make a plot of just a one-dimensional plot of what the probability distribution looks like, say, for M1. This is P of M1, and we can have, here's the most probable value, and we're most likely, we're most probably, let's say, 90% probability in that particular range. Okay, so we want these outputs. How do we calculate this? Well, we have a likelihood. So that is saying, assuming we had these parameters, what is the likelihood of getting this particular realization of the data? Okay. This depends on understanding the process we have going on. In our case, we make the assumption of Gaussian noise, so we end up with a Gaussian probability distribution going into this term here. We have a prior. This is what we assume about our parameters before we had the data, and we typically assume a non-informative prior in the LB case, so we don't put any strong assumptions into this. We spoke last time about how we can put in different prior choices, so perhaps using one informed by the population. Perhaps alternatively, we could say, let's assume we do know the true physics of the source formation. We could put that in and say, given that, what do we understand about the source? But we have some prior distribution, and we're going to talk, we're going to see today some of the importance of this, and highlight again why it's important that we have a nice uninformative prior in the LBK analysis, so people can use our results. And then we have a term on the bottom, a normalization term, that's the evidence, which is the marginalized likelihood. So we take the likelihood here, multiply it by the prior, integrate over all values of the parameters to get the probability of getting this data realization given our prior assumptions. Okay. Now, generally in parameter estimation, we don't actually need to worry too much about this normalization constant. If we only care about the shape of distributions, we can take care of normalization at the end. But we will see that this is very important when we want to do population inference. Okay, so we spoke about this as parameter estimation, and then I highlighted briefly how we change this to the question of doing population inference. So in this case, instead of inferring our set of parameters for an individual source, we're going to be inferring some hyperparameters, which are called lambda here, which are the parameters of our model. So they might be our power law slope alpha, they might be the mean of our Gaussian, the width of our Gaussian, say if we have a power law plus peak model, might be some parameter for a power law of redshift dependence. It could be whatever we want, but it's some set of parameters that will describe our particular model. And we want this given the set of observations. So not just one signal, but the set of them. Okay. So we want to calculate this posterior now. And so we have an idea that, okay, we're probably going to want to use Bayes' theorem again to do this. So we want to have some likelihood, probability of getting this data set given our model parameters, going to have our hypermodel parameters here, our model hyperparameters. Some prior on our hyperparameters. That could be something quite simple, could be a uniform distribution and alpha, say, go for something uninformative, or it could be something which is inspired by astrophysics. So we could say that if we assume our Gaussian component represents the pileup of masses due to pulsational pair instability, we know that should be about 35 solar masses or so. So we could put an informed prior, say, it should be 35 plus or minus 10 solar masses or something. Again, prior choice up to the user, but it will affect the interpretation. And then we're going to have a new evidence term at the bottom with the probability of getting all this data, which will, again, turn out to be a normalization, so will be less important for getting the functional form than this. Okay, so this is what we want to do. And what I want to spend some time going through today is how actually we calculate this. This is a little bit involved, so it'll be a little bit of algebra, but we'll try and go through it, and hopefully along the way you'll see some of the important steps and learn enough that you might be able to go away and perform such a calculation yourself. Although, as always with these things, generally there's a bit of a step between having a look at the equations and then actually typing up some code and performing an analysis. Okay, so this is the plan for today, how we work out this, and at the end, this is we should have an idea of how these population inference results are presented, how those were calculated, all the ingredients that goes into them. Okay, so let's start. Okay. We know we want to end here, but let's start for a second just at this single parameter estimation result level. And let's rewrite this slightly differently. What we are actually assuming when we do this, as we have some prior here, and this prior we can write as being given some model choice. Okay, so I'm using M here to denote a model choice. So we have some prior given M. Okay, our likelihood is the same, but it's also given our choice of model. We have then the evidence for that particular bit of data given the model, remembering that the evidence is calculated via this integral, so it depends on the prior choice, so that's why the dependence on the model comes in. And at the end, we get a posterior on the parameters given our data and our choice of model. Okay. And what our model here encodes is just our prior assumptions about the parameters. So the uninformative choice of priors, the uniform distribution of masses and so on, is a particular model choice. And so our LVK results are always quoted, what's the probability of these parameters given our model choice of an uninformative prior. Now, in the case of population inference, what we want to do is assume a particular model. Okay, we're no longer assuming the uninformative prior model, which is one particular model. We're now assuming that we have some model, which is going to be some parametric model, some functional form. So it's described by a set of parameters. Okay. So we have going from one model which is fixed to one which varies depending on the particular choice of hyperparameters. And in this case, we realize that what we would have for our particular realization is given our posterior given one particular set of lambda. So one particular set of hyperparameters is our posterior distribution. So if we wanted to, we could calculate this posterior distribution one at a time for each value of lambda. So we could, put in one particular realization. So one particular value of the power law, the mean, calculate this posterior distribution, putting in a different prior. Then we could try another one and another one and another one and get many different posterior distributions. Okay, I've got a question here. Okay, so question, does the model hyperparameters set include hyperparameters for different models, or does it represent a single model choice? This is a good question. So what can we include in lambda? Potentially, we could include many different things. So here I'm going to assume for simplicity that it's fixed for one model. So we're picking, say, the power law plus peak model that we spoke about last time, or the power law plus spline model. If we wanted to, we could include an extra hyperparameter that describes the model choice. So we could have a particular variable, let's call this, say A, which if A equals 1, that implies we're in the power law plus peak model. If A equals 2, this could imply the power law plus spline model, and so on and so forth. Then we go through these. In practice, this is extremely difficult to implement in a realistic way. So one would not normally do a level of hyper population inference where we change the model like this, just because of the computational complexity of this. It's possible to do. You can write down the equations, but it is somewhat more complicated. So in this particular case, I'm just going to take the model is fixed, the particular phenomenological form is fixed, but changing so varying the hyperparameters to see which hyperparameterization best fits the model. Okay. So where were we? Okay. So yes, we could calculate this posterior distribution now for any particular choice of our hyperparameters, which is great. Now, looking at this, you'll hopefully notice that we have our evidence written as P of D given lambda, and this is the same form as what we are looking for our likelihood. The difference here is that this is for just one data set, whereas here we want the entire data set, but you can see they are the same form. So what is in fact the case is that our evidence, so our parameter estimation evidence, becomes our pop inference likelihood. Okay, and this is why population inference is often also referred to as hierarchical inference, because we have a hierarchy of inferences that the evidence from one level of inference becomes the likelihood to the next level up of inference. Okay, so let's delve a little deeper. What do we want? Okay, so given if we just had one observation, okay, we could calculate what is the probability of our set of hyperparameters given our data. Using Bayes' theorem, we know that would be our likelihood, probability of the data given that hyperparameters, times suitable prior, times some, so divided by some normalization constant, which in this case, by analogy to what we had before, would be the integral of PD of lambda, P of lambda over. Okay, so we would take our evidence from parameter estimation, that becomes our new likelihood, and we could work out our population parameters. That's if we had a single observation. We want to do this when we have many observations. So how do we generalize things? Well, what goes on is that the probability of getting our data set given our model hyperparameters is just the product of the individual likelihoods. assuming that we can take all the events as independent of each other, which should be a reasonable assumption that we don't expect a causal link between the gravitational wave. Okay, so we can multiply these all together and then substitute in to our term above. So what we want, probability of lambda given our data set, is going to be this product given lambda. I'll put that in brackets just so we know which term is the product, times the prior, and then we need our normalization constant at the bottom, okay, which again we can also work out that well, it's just going to be set the integral here, so we substitute this into this, and we get the ensemble set. So let's write that down for you. Integral P D given lambda P. Okay, so we take all of our evidences, multiply them together, put in our prior, normalization constant, not too important for the mapping out the probability distribution, but we can calculate that. Okay, this is the idea. Everyone happy so far? Okay, so now the question is, how do we actually, oh, sorry, go ahead.
Yeah, I have a small doubt. So for population inference, what is your data? Is it still the time series trained data, or is it some sort of a posterior that you get from parameter estimation?
So it's the selection, it's the combination of the different time series. So the time series associated with each event.
Thanks.
But we see we don't act when we do population inference, assuming that parameter estimation has already been done. We don't need to go all the way back to the data. So let's take a second. We spoke about if we wanted to, we could go back and do parameter estimation, do this inference for each value of lambda. So each model parameter we came to consider. Now this would be extremely computationally expensive, right? Parameter estimation takes at least a few hours, even in the best cases. In the worst cases, extreme, weeks to do this. And we want to do this for each value of lambda. And if we're considering, thousands of different values of lambda, hundreds of thousands of different values of lambda, because we're in a high parameter space, that becomes completely computationally infeasible. So can we do something else? The answer is yes, thankfully. So what do we do? Well, let's just I'll take a step back for a second and talk about what is our posterior distribution. So in general, our posterior distribution, P of theta given data, and I'll just put that as our default model for now. Okay, what do we have of this? This is represented by a series of posterior samples. So this is a set of posterior values. So we have a point here, theta k, being representing the case sample drawn from this distribution. So it will be, this is a vector which contains, well, an array, I guess, so, of masses, spin values, and so on and so on. And so our posterior distribution is a whole list of different posterior samples. And then, so if you were making a plot of posterior samples, so let's say we have M1, M2, we would have posterior sample in many different places. And by looking at the distribution of these at places where there are more and fewer, this reconstructs the probability distribution. So if you were to histogram this up, use a KDE, some form of density measure, to go from samples to a continuous distribution, you'd reconstruct your probability distribution. So we could reconstruct some contours around this. So that would be our probability distribution. So the output of our sampling algorithms is a set of posterior samples drawn from this distribution. Hopefully you've had some examples working with posterior samples as part of your tutorials. So this kind of is familiar now. Now, a nice property of probability distributions in general is that if we have a variable x, so, and we want to calculate its expectation value, I'll denote that by angle brackets, then all we need to do is take the value of x at the particular parameters of interest and multiply this by the probability distribution. So that would be our posterior distribution here, and then integrate over all values. Didn't quite leave myself enough space, but hopefully you can still read that. Just integrate over all values. This might seem a little odd, but this is, if you've not done much with probabilities, but this is just a sort of definition of an expectation. You have your value, weight it by the probability distribution, and integrate up. Might be more familiar if you've calculated averages in the past to think of this as a sum. You sum up all the values, divide by the total number of samples, and get the value. And in fact, this is how we calculate expectation values with a set of posterior samples, that we can replace our integral over the probability distribution with a sum over posterior samples. So if we have a bunch of posterior samples from k, little k equals 1 up to big K for the total value, this would become the value of x evaluated for each posterior sample, and then divide by the total number of samples. So our expectation value, just add up all the value of x's we have, divide by the total number. Okay, hopefully that's fairly familiar to you. This is entirely equivalent to this. So this means whenever we have an integral over a posterior, we can replace it with a sum over posterior samples. And this helps because we can replace some of the terms we need to calculate for our population inference with some sums over posterior samples. Okay. So let's go back. Let's take a look at what we want here, our likelihood for a single event. Okay, we want probability of data given lambda. Probability of data, probability of data given lambda is the integral of probability of data given some particular value of theta, our likelihood, times pi over theta given lambda, integral over d theta. That's just going back to our original definition here, but now putting in our explicit dependence on lambda. Okay, so this is okay so far. What we can do here now is use Bayes' theorem on this term here. Okay, probability of d given theta, okay, is this term here. So if we rearrange our equation, we can write this out as probability of theta given d, and I'm going to put in a default prior choice, which I'll denote here as our m again. Okay, and I'll put a little subscript of a 0 out there to denote it's our default model used in our LIGO-Virgo-Kaggle analysis, our uninformative priors, as opposed to our lambda model, which we're using for our hyperparameterization. So P of theta given d and our default prior are, so multiply, so that's this term, multiply up by the evidence, so P of theta given our default model, and then normalized by our default prior. Okay, so I've just replaced this term here by substituting Bayes' theorem here, and then weighting by our different prior. Okay. So just expanded this term using Bayes' theorem with this particular prior form. Okay, why is this good? Why did we bother doing this? Well, now you see we have an integral over a posterior distribution. Oops, I missed out a, sorry, this is a d theta, not a d lambda. We have an integral over a posterior distribution of this other term here. Whenever we have an integral over a posterior distribution, we can replace it with a sum over posterior samples. Okay, so let's just rewrite this to make this slightly clearer. Okay, up first, let's move this term, the probability of the data given our default model choice. This doesn't depend on theta, so we can move this outside the integral just to make life a little cleaner. Okay, then let's have our integral. Let's write our posterior here. And then we have the thing we're multiplying by, which is the ratio of priors. So it's this prior divided by this prior. That's what we have. So if we compare directly with what we had earlier, expectation value of x is just the integral of x multiplied by the posterior over all values of theta. Well, in this case, so here's posterior, here's x. X takes on the form of our ratio of priors, integral over all d theta. So we can replace this as our prefactor out the front. Then we have our 1 over k sum over all values of little k of the ratio of our priors. Okay. So evaluate this ratio of priors for each posterior sample, add those all up, divide by the total number of samples we have, multiply by our factor out here, which gives the normalization, and this now gives us our likelihood for this single event. So instead of having to recalculate parameter estimation for each value of lambda, which would be extremely expensive, what we can do is we can take our default parameter estimation with our standard LIGO-Virgo priors, evaluate the priors of our hierarchical model at that point, take the ratio of the priors in our uninformative prior at that point, just add those up all and reweight everything. So we can recycle the posterior samples, reweighting them instead of performing parameter estimation all over again. The important thing to be able to do this, of course, is we need this ratio, ratio here, to always be well defined. So we never want this P of our default prior, a P of theta given our default model, going to 0 at a region that is interesting for our parameterization with our hierarchical model. This is why it's very important that the LIGO-Virgo-Cagra analysis is performed with broad, uninformative priors that have support across parameter space, because we want to be able to reweight them to whatever prior we have. Okay, should it be P of D? Yeah, I guess. No, so question is, should this be P of D given theta and lambda at this point here? So I guess, yes, that would be a clear way of doing it. But what we're saying is that the data doesn't actually depend on this value of lambda in that way. We're using this to expand out. We can do this however we like, subject to this. Let me see if I can think of a good way of explaining. Yeah, so assuming that we do have this condition here, that we can do this reweighting, that we can, we always have posterior support. We also have prior support in the regions. We can do this substitution at this point because the exact distribution shouldn't, of the exact likelihood, shouldn't change depending on the particular assumed model here. So as long as we can do the substitution later on, which is a bit circular. So as long as this is, but as long as we can do this reweighting, we can switch in this form for the posterior here, because this doesn't depend directly on the assumed prior, providing we're not truncating the posterior distribution in that form, because this is the probability of the data. Okay, so that might take a bit of thought. I don't think that's a particularly intuitive way of understanding that. But you can hopefully also see that this works out just if you were trying to recalculate. Oh, actually, do I want to miss it? No, I think that's okay. Okay. So yes, good question. I think as long as we have this sufficient support, this is all okay. Okay, where were we? So we have probability of this particular realization of data given lambda. We can calculate probability from our original set of samples. Therefore, we can work out the ensemble probability of all our data, probability of lambda given our complete set of data. Yeah. What we want is our likelihood. So our likelihood here, we need to take the product for each one of these. So our probability of our ensemble of data is going to be the product of all of these. So if we use I to index all our events, it's going to be the individual evidences under our default model, our sum over each of the kappas and I'll put a little subscript I on just so we know that the theta are labeling the theta event. Okay, so we take the product of all this for all of our individual terms, and that gives us the likelihood that we want now for our population inference. Substitute this in, multiply it by a prior, and we have a normalization constant at the bottom. And that's what we will need to map out our probability distribution. So this is the basic idea of the hierarchical inference, that we reweight by different priors, and that allows us to calculate the likelihood for given events. So we don't need to go all the way back to our data stream, but that gives us all we need to do to calculate our hierarchical model probability distribution. However, we have neglected something kind of important at this point, which is the selection effects. We spoke about selection effects earlier on, that it is important to account for selection effects, because if we see, well, actually, if we do see many events, so here's, so looking at total mass of the system, we have lots of events at some total mass, few events at other total masses in our observed population. So our observed population has some distribution like this. That doesn't actually mean the astrophysical distribution is the same. If we're much better at detecting systems at high masses than we are at low masses, the true astrophysical distribution could be something more like that. It's just that we detect more of these. So we need to know what's the probability of detecting each system to properly account for selection effects. So we've not included the selection effects in our analysis so far. So this is what we need to add in. And this will turn out to be can be added in by renormalizing our likelihoods to consider just the set of data that we could detect. So up first, I want to just define a probability of detection. I'm going to use a big P for this, although you might not be able to tell from my handwriting. So if we have a source with these parameters, what's the probability it is detected? Well, we have the likelihood of getting some data given that value of theta, and then we integrate over all possible values of the data, okay, DD, over just the range where we have detectability. So if you like, we could just be, say, detecting over the range of values where the signal to noise ratio is higher than some detection threshold. Or as we spoke about previously, we have some ranking statistic that's called a p hat, which is a combination of the SNR and the consistency test, and depending on the background, when this is greater than some threshold. So we take the likelihood, integrate over all possible realizations of the data with the constraint that we are detectable. So we have some detection threshold greater than this value. Okay, and what this gives is a new likelihood. If we now renormalize things, what's the probability of seeing this set of data given source parameters and the knowledge that it was detected? Okay. So probability of seeing this is now just our usual likelihood, but renormalized by 1 over p det. Okay, if the data was a set of the detectable data and 0 otherwise. So if the ranking statistic turned out to be greater than the threshold, say, it's our likelihood, but normalized, so it will still integrate up to give the right value, and 0 otherwise. Okay, so first correction, how we could write down a likelihood for a single event being detected. But now let's move on to consider what's the probability of seeing some data given our model parameters and the fact that we have a detection. Okay. We're going to do this analogously to here, that we're going to add in a new constant that will take into account the renormalization. So let's define a variable alpha, it's alpha det, that depends on small number, analogously to how we defined p det for this value. So we're now saying, what's the probability of getting some detections given this hypermodel? Okay, you can imagine if you change your hypermodel parameterization, so if you change the slope of your mass distribution, you have different fractions of your population being detectable. So this is what information that this is encoding. Okay, I'm going to define this in a similar way. That what we're going to do is we're going to take p of d given hypermodel parameters, and we'll integrate this over all the possible data realizations, but again, only over the set of data that gives us detections. So we're integrating just over the detectable regions. Okay, we can expand this out. Okay, so I'm going to move my DD here. So integrating over all detectability. We expand this out using our standard form. Oh, I've lost the piece of paper. So, using our standard way of marginalizing our likelihood. So this here, P of theta, is P d given theta, P theta given lambda, integrated over all values of theta. We can now switch the order of our integrals. Integrate over d theta first, then integrate over all the different realizations of data of PD given theta, P theta given lambda. Okay, and this term here, hopefully recognize, is P dat. So this is the integral of the P theta of P dat theta times our prior over lambda. Okay, so this is saying alpha, which is we wanted to be our term that encodes how detectable is this population, is just the weighted integral of all the different detectabilities weighted by the prior of having those choices. So P det, we know, is the probability of, if we had this source parameter, how detectable would this be? And then we take a weight of these based on our prior. So in our population, this is how many each value of theta is. Integrate that over all values of theta, and that gives us alpha det. Okay, I think there's going to be a question there. No, okay. So alpha here determines the detectability of our population. We're saying we want to calculate a new likelihood, probability of getting the data given our value of lambda, and the fact we have a set of detections for this. We think we're going to renormalize things by this weighting. How do things actually work out? Okay, so new piece of paper. Okay, the form of P det, PD that we want, given we're only considering the detections we have, is going to be 1 over alpha det lambda, okay, times our usual P d of lambda. Okay, so just in analogous way here, we can define our changed P det where we renormalize here. We're doing the same here with alpha, and now if we expand out this here using our usual integral, and I thought of a much simpler explanation for the earlier question of why does it not matter whether this depends on lambda or not. And this is because I wasn't thinking of this earlier, so it's a bit slow, but that just depends on the form of our likelihood. So P of d given theta is just the property of our noise curve. This is saying, given these values of theta, what's the probability of having this value of the data? This just depends on the noise properties of our detector. Like, it doesn't depend on our model choice. As long as we have can be in the right range of, as long as we can have this range of theta, it doesn't depend on the noise properties. We always calculate it the same way. It's always this Gaussian product. So that's why much earlier on, much earlier on, it doesn't matter if we So we want to explicitly write this down. Okay, this is why this doesn't depend on whether we put this down as a function of, so given lambda or given n naught or anything, because this is always the same regardless of which model we choose. It just depends on the properties of our data, our detector data and our detector noise. It doesn't depend on the assumed astrophysics at all. Okay, so here's now our renormalized likelihood taking into account selection effects for one event. And now if we move forwards to consider our ensemble of populations. What are we going to have? We're going to have 1 over alpha det lambda here, and then the product of all of these for our individual events. P R D given lambda. Okay, and this might make a bit more just intuitive sense if we write this out now. What do I want? Alpha. Just substituting in for alpha is here. We can get a nice symmetry that on the top we have the likelihood for likelihood for the individual event multiplied by the pi, and on the bottom we have the probability of detection given those times the pi. So this reweighted posterior taking into account selection effects, basically just multiplying into the detectability of the signals. Okay, now how do we calculate this in practice? Okay, so let's assume now we're taking into account the number of detections we have. If we have an astrophysical model with an average rate mu of signals, and we detect n of them, probability of having n is just given by something like a Poisson distribution. So a Poisson distribution would be exponential of the rate to the n, and then we would divide by n factorial if we had a Poisson distribution for all the different combinations. In gravitational waves, we can tell our observations apart. They're not indistinguishable, as is the case when assuming a pure Poisson distribution. We can tell GW 170104 from GW 17817, for example. So we don't have the same indistinguishability, which means we lose a factor of n factorial in this probability distribution if we consider all the different possible permutations. So we don't care about the actual order they happened, we just care that they did happen. So we have no over n factorial here, because we consider all the different permutations, but this is the probability of getting n detections given average rate of mu. If you're not convinced about the loss of n factorial, it doesn't particularly matter, because we're only going to end up caring about the functional form, the proportionality, not the overall normalization constant. But this is probability of getting n detections given a detection rate mu. How do we calculate what mu should be? Well, mu, the number of detections we expect, okay, going to be set by the rate of events, r, multiplied by the number, so multiplied by the distribution of events, so theta given our model. So this tells us how many models we have with each value, normalization constant here for representing the total number, and then the detectability of detecting each one with that set of parameters. Integrate that over all values of theta. So the rate of signals we expect to see, given by the astrophysical rate density times the detectability, integrate over all parameter space. Okay, everyone happy with that so far? Expected number of events. This we might recognize as something we've seen before. This value for mu is just the same as alpha, except we've multiplied by an extra factor of r, this normalization constant that gives us the total rate. So our expected number of detections, just the rate times alpha in this particular model. Okay, so now let's, sorry, what's the question?
Shouldn't your rate also be a function of theta?
Sorry, can you repeat that, please?
Yeah, shouldn't your rate R also be a function of theta, and then you cannot write mu is equal to R alpha?
So excellent question. So this way of decomposing the rate into an overall normalization factor times the distribution of parameters means we can split it up. So this is just the normalization constant. This is the overall rate. So let's take a second to talk about this a little more. The rate is, let's call that the overall rate n, will depend on the theta. So the rate of events with a particular set of parameters will be depend on theta and our model choice. Okay, and we might be able to make a little plot of how many we expect here, and we might expect something like that. Where I'd say this is mass. This is our rate of seeing things with different masses. Okay, we can always write this as a probability distribution for the different values of theta multiplied by an overall normalization constant. The probability will always integrate to 1, and so the R just gives us a total rate after integrating out that dependence. So we can always split the rate into an R which doesn't depend on parameters multiplied by a distribution that does depend on parameters. And that's what we've done here.
Understood. Thanks.
Okay. But this is leads us on to a second point, which I've been slightly loose with my notation here. That in theory, our hyperparameters for our astrophysical model really are two. They're of, so we could denote this as a big lambda, I guess. Big lambda, which equals a set of parameters that describe the shape of our distribution, which I've always been using as little lambda so far, plus an overall rate. So whenever we're really doing a hyperparameter inference, we really want to have both the shape parameters and the overall rate. So this is what we want to calculate now. Okay. Inference of both big lambda given our data set, which is equal to inferring both R and little lambda given our data set. Okay, so was there another question? Okay, so we want to infer both the rate and the shape of our distribution. How are we going to do this? Well, I'm going to go straight into a proportionality here, because otherwise it's going to be a bit too much to write everything there. So this is going to be proportional to the probability of getting the number of events we have given our lambda times a prior on the rate multiplied by probability of getting a particular set of data we have given shape parameters and our detectability, the fact that we detected them all, times some prior on these shape parameters. Okay, I should say there, where our data set, so n, if it wasn't clear, n is our number of our detection sets. So di equals d1, d2, d3, all the way up to dn. Okay. So probability of having a particular rate and shape given our data set, probability of getting this number of detections, which depends on the rate, and the probability of getting this particular shape, which depends on the detectability of these detections times that. Okay. So let's substitute things in now. We know that our probability distribution here, probability of getting n given r and our shape parameters, is given by the exponential of mu times mu to the n. And we know that mu is r times alpha. So we're going to have exponential of minus r alpha det. Alpha is a function of lambda, but I'm not going to write that down because we're going to run out of space otherwise. Multiplied by mu to the n, which is just going to be r alpha det to the n. Okay, and that's going to be then multiplied by our prior on the rate. Okay, that's taking care of these first terms, and now we're going to need to multiply this by probability of getting this data set given our shape parameters and the fact they're detected times some prior. This is what we were working on earlier. This form here. Okay. Oh, and sorry, I miswrote this. The product goes on this side. We need the detectability on each term. I wrote it correctly here. Okay, so that's this term here, this probability, this likelihood for our data, okay, is product with I to n, I equals 1 to n, of integral p di given theta, p theta given lambda, divided by alpha det, okay, times our prior on lambda. Okay. So expanded out this term here using our almost Poisson-like distribution and our expected number of events, which depends on detectability, times our likelihood for these shape parameters, which is what we were dealing with previously, adding in our detectability, times our prior on those shape parameters. So we can tidy this up slightly because we have alphas here and alphas here. We can write this as x minus r alpha det r to the n. Then we have alpha to the n, which will cancel with this product down here. Okay, so we're left with just the product from I equals 1 to n of the integral of the I given theta, p theta given lambda, times our two priors, our prior on R and our prior on our shape parameter, hyperparameters lambda. So this is the full way to do hierarchical inference of both the rate and the shape of our distribution, which we should do an exponential term, R to the n term, this product of individual data terms and a bunch of priors. Okay, we're doing okay. Now, to make life a little simpler, a common assumption, we don't need this to be true, but this will make certain things a bit easier. And if you are reading papers, you will often see this and the equations that follow. So this explains where it comes from. A common assumption is that our prior on the rate is a 1 over r prior. This is often known as a Poisson Jeffreys. Is that the case? Oh no, I think that's the square root. Ignore it. Not often known as that. This is a log normal prior. This is a nice scale invariant prior, basically saying uniformly distributed in log. If you have no idea on the scale of your rate, that will be a good prior to use. Numerically, there are some issues associated with this, as this goes to infinity at 0, but we're going to ignore that for now, because if we plug this in to this equation up here, our posterior for everything, given our set of detections, is going to be proportional to exponential minus r alpha det r n to the minus 1, we'll multiply in by our prior, and then multiply this by our product, and our remaining prior over our other hyperplane. Okay. We can now integrate out our dependence on the rate. So our detected, so if we just care about our shape parameters and not the overall rate, which is not always the case. Okay. If you remember when we were speaking about the predictions for different channels, we did say that different channels produce different rates. And so there is information from the rates that is important and informative. So we don't always want to do this, but sometimes we do. Sometimes it makes life easier. So I want to show you how to do it. Probability of just having lambda, so just the posterior on lambda, we can get by integrating the posterior on the rate and the shape hyperparameters given our set of data over all values of r. So this is called marginalizing outputs, integrating out which we're not too interested in. So we want to integrate the term above with respect to r. Okay, and to do this actually makes life a little easier to go and substitute some things back out. So we simplified this a little bit. I'm now going to complicate it a little bit, but trust me, it will get a little bit easier at the end. So I'm going to move my dr to the front here so I don't forget it and leave this integral unclosed. What we have here is exponential minus r times alpha det r to the n minus 1 times our product I equals 1 to n of everything here, integral p d I theta p theta lambda. Oh, I forgot my, it's why I need to, it's this here needs a d theta, and here this needs a d theta here, integral there, and then the p lambda at the end. Just for that number piece. We're going to simplify this slightly by moving the alpha det out of back into this term here. So undoing the simplification we made back here, where we noticed we had an alpha here and an alpha here that cancelled out. Going to substitute those back in. So dr exponential r alpha det. Okay. Then going to have an alpha det times alpha det r to the n minus 1 multiplied by the product equals 1 to n integral p d theta given lambda, remember the d theta this time, all over alpha det times our time on alpha. Okay. So I have alpha det to the n minus 1, alpha det to the n, cancelled out by the alpha det down here at the bottom. Okay. What we can do here, just to simplify things slightly, it's complicating things to make them a little simpler. Let's change from working in terms of R to working back in terms of mu, our rate, which we know is R times alpha det. So this integral here is just equal to an integral over d mu exponential of minus mu to the n minus 1. So that's n to the minus 1, and we have an alpha times the dr to give us the d mu. Times, can I fit it on the same line this time? Let's be brave. I equals 1 to n of this term here, integral p d I given theta, p theta given lambda, d theta. No, can't quite fit it all on one line. Alpha det multiplied by pi over lambda. Okay, so looking at this now, we have an integral of exponential of minus mu to the n minus 1 times a bunch of stuff that doesn't depend on mu. This is going to give us something which is like n to the minus 1 factorial, and then the product of stuff that doesn't depend on mu p di. Just fit it in this time. Okay, so another constant of proportionality out the front, and what we end up with is this term here, which is a product of our individual detection, individual likelihoods for the events normalized by our constant at the end. Okay, so this is just a number here. So if we're only caring about proportionality, we don't care about this. So we have this term times p of lambda. What is this term? Well, this is what we just worked out a really long time ago. It's just our standard detection likelihood. So if we marginalize out over the rate, so if we don't care about the rate, and we assume this particular prior of 1 over the rate, which is a nice scale invariant prior, we end up that our posterior over lambda and delta is just proportional to what we worked out earlier. So this is why the rate can often be marginalized away to give a very clean result at the end. Okay. So that's a lot of algebra. Given this formalism, we have a way of working out probability distribution. We don't have to marginalize out over R. We can work out the number of detections we have. It depends on our distribution of sources, depends on this likelihood term here. This likelihood term here, we can calculate thanks to the posterior samples we have, just reweighting those. So we can substitute in this form here into our equations up here. Calculate this as we want to, and this gives us our hyperposterior. So that's everything I wanted to go through in terms of the algebra here. This was the most algebraically heavy part, but hopefully that is useful to you. Was there a question there? Okay, so we came a long way. So just to recap, we started off with just Bayes' theorem. We talked about this in the particular case of an individual event and how we work out the source parameters. We then went up a level. This is a hierarchical inference. Said what is the properties of some hyperparameters given our data set. For a single observation, we could just redo parameter estimation with a different prior and get the results out we had. When we have an ensemble, though, we need to multiply together. But when we want to map out many different values of lambda, that becomes computationally prohibitive. However, we can reweight our posterior samples from our standard likelihood, standard parameter estimation analysis to the new prior, the one given by our population inference. So we can recycle things, save on computational expense, provided that we pick sufficiently broad priors in the first place, so we can do this reweighting. So now we can evaluate our likelihood for different values of lambda. We just need to reweight our posterior. If we have many detections, we multiply together the individual likelihoods for each event, and we do the same sort of thing. Okay, so this is the overall idea, but we've not included selection effects. When we want to go and include selection effects, we need to renormalize things. So we introduced two variables to take care of this. We introduced PDET, the probability of detection for a particular set of parameters, so we can renormalize our likelihood at the event level. And we also introduced alpha that, which I have somewhere here. No, that's not it. Okay, which I have somewhere, and hopefully you have in your notes. Yeah. Okay, I've lost alphabet, but we have somewhere. Oh, no, it's not there. Yes, last place on it. Okay. As a bonus tutorial question, you can try and calculate the selection effects for me finding the right piece of paper, given the number of pages I have. And that should be a nice uniform distribution, but maybe it doesn't work out that way, given it's always the last piece of paper. Anyway, we have PDET for this, talk about a single event given the source parameters, what's the probability of detection, and we introduced alpha det, which is given a population, what's the probability of finding things detected. Given this, we can account for selection effects. We can account for the fact that we're only analyzing the data for which we have detections. We're not looking at the entire data set, we're just looking at the detections. We come up with a renormalized form of the likelihood. Okay. Okay, so we add in this renormalization, we end up with this nice product term where we're weighting by the detectability term. Given this, this is our likelihood for our events. In general, we'll want to infer the probability distribution for both rate and shape parameters of our distribution. So we spoke about how to calculate this. This has two components. One, something that looks like a Poisson distribution, which gives us the rate information. Okay. What's the probability of getting this many detections given the expected number of detections? Here we calculate the expected number of detections. We work out it's proportional to alpha det with this crucial bit of extra information, the rate, which is the information we want. Okay, so we can calculate this bit, and here is our probability of getting these detections given our shape parameters, which is what we calculated earlier. So we can write out this big functional form. When we come to calculate it, we're going to need to substitute in with our sum over posterior for this term here, but this is what we want. Okay, here's a nice term. In the particular case that we have a prior 1 over r, we can marginalize out over the rate, and this simplifies the functional form. So we end up with something which is basically just like this term here that we calculated there. Okay, so that's the theory behind how we do this. The input to this type of analysis will be our sets of posterior samples and some measure of our detectability, so some measure of our selection effects, so we can calculate alpha delta. Given this, we calculate posterior distributions over the hyperparameters lambda, get the rate information, and that's how we infer the rates. So when you're looking at these Lively Virgo Cagra papers, you'll often see plots showing probability distributions over parameters like the power law index, maybe have posterior distributions on the rates. This is how they're calculated.
I have a question.
Mhm.
So what is the motivation behind choosing a log uniform prior for rate parameter? Is there any?
Excellent question. So yes, why do we do this? So there are two reasons for doing this. One is it makes this calculation a bit easier. So it makes the marginalization quite simple, so we can get away with the mathematical trick of making our life a bit easier, gives us a nice functional form. That's one reason why we do it. Another is because a log uniform prior is quite a sensible prior. If you don't want to put in too many assumptions, but you have no idea of scale. So if you don't know what the rate should be, okay, you don't know what the rate should be, okay, one could argue that it's equally likely to be, say, between 1 and 10 as it is between 10 and 100, because we have no idea of scale. So we'd want a uniform distribution over these scales. That is the same as uniform in log, which is the same as 1 over r. So if you have no idea of the scale of anything, uniform in log is the sensible thing to do. So you'll quite often see priors like this for scale parameters, things that control the absolute values of things. So it's quite a common prior as well for using for the standard deviation of a Gaussian, for example, if you've no idea what that should be, because that sets the overall scale. It's not such a useful thing for things, say like where you know it could be positive or negative, obviously, but for things with just a magnitude, it's quite sensible.
Thank you.
Yeah, I have one clarification and one question. So the clarification is in the latest LIGO-Virgo population paper, is the marginalized likelihood over R used, or is the full likelihood used?
It's a good question. I'm pretty sure by default we often use this marginalized over rate. However, we do also recalculate the absolute rate parameters. So in that case, you can't be marginalizing over rates.
Right.
I think you'll need to double check to look at the exact analysis that you're interested in. In some cases, we want to get the posterior over rate. So, you know, P of R given and our data set, okay? And if you're getting this out, you know, some probability distribution on what that looks like, you can't be marginalizing R out. You can't have integrated out because you need that information somewhere. So in that case, it won't be marginalized out. I think some analyses do it, though. It is quite common in the literature, which is why I wanted to point it out and explain where that comes from.
Yeah, I think the corner plots do have rate as one of the parameters, so it's probably not marginalized on. So my question was about the p-det, the definition of the p-det. So there you've sort of put like a hard cutoff at, let's say, whatever, SNR equal to 10 or whatever. But then if we wanted to include, and I know there are analyses that include, you know, sort of marginal events as well, which are close to 10, say, how would you systematically include that? What is the rough prescription to that?
Yes. Okay. So I think there are two levels to this question. So one is, how do we actually impose this detection threshold? So I want to just take a moment and speak about this and a common approximations people often use. People will often use a simple signal to noise ratio cut for this. Okay. Which we know is a bit too simple because we don't actually cut on SNR most of the time. We cut on the detection statistic. But we could equally, I mean, there's nothing stopping us doing a search which is just SNR limited. In effect, and if you look at some of the LIGO papers, we often do curate a set of samples which are cut on SNR. It's not as simple as that because it's SNR of things found by the search. So it's really both an SNR and a false alarm rate cut. So we're not including glitches in that. So that's, you know, a little bit of an approximation, but it's handy when doing simulations of data. If you're simulating signals and you're not putting any glitches in, you should get the selection effects calculated correctly because you're only considering signals in that case. So step one, you can use quite simple cuts. Step two to realize is that the detectability is always just a function of the data. So you might be thinking, okay, if I inject a signal, so if I make a fake signal with an SNR, an optimal SNR, so you take the noise weighted inner product of the waveform with itself, inject that into some real data, the SNR you calculate, then what we call the matched filtered SNR, is going to be plus or minus a bit from the optimal SNR because of the noise can either add or subtract from that. So really, you should not be using the optimal SNR for this calculation. You shouldn't be using the SNR calculated from just the waveform. You should add in the noise realization. So you should only use the matched filtered SNR, the SNR you get when you take the template and match it to signal plus noise for calculating these selection effects. That's the proper way to calculate these. Quite a lot of papers only use the optimal SNR because it's easy to calculate. It's a reasonable approximation, but it's not exactly what you want to do. And if you want to do a careful analysis like this, you need to use the actual selection effects. So this is actually why the results of injection campaigns, so whether the false alarm rates calculated for a bunch of simulated signals are produced and released with LIGO Virgo catalog, so you can actually calculate the actual selection effects. You don't need to put on a toy cut here, but it just does depend on the realization of the data. It can be just a binary yes or no. Okay, so that's first part of the question. And then I think the second part of the question is something more subtle, which is, what if we're not saying yes, no, it's detected? So what if we're not saying, let's take everything with, say, P astro greater than 0.5 as real and everything below as not real? But what if we soften that and say, what if we don't detect, but we weight by the probability? So we say things with a probability of being, P astro of 1, we assume are completely real. Things with a P astro of 0.5, we go, okay, they may or may not be real. So we want to weight them accordingly in our analysis. I think that was the question you're really getting to.
Yeah, that was the question.
Yes, so that complicates things quite a bit more. And so I purposely did not go into that because we wouldn't have time just within this one lecture to go into this. There are some analyses that do this. There's a couple of papers, one from the Monash group, one from the IAS group, which you'll find cited in the various LIGO Virgo CAGRA papers, and I'll add some citations to the slides so you can look it up, where they introduce a formalism to weight by P astro. There's some mapping between the two formalisms, so I think they're roughly equivalent to each other. I prefer the explanation given in the IAS paper in terms of the derivation of this. But yeah, you need to recalculate alpha in a weighted way to take into account this probabilistic way. And it adds in quite a few subtleties to the calculation. So there've been very few analyses which have actually tried to do this, and the LIGO Virgo CAGRA analysis don't do this yet because of these subtleties and agreeing how to do them. But yeah, you need to weight your alpha accordingly in a slightly more subtle way to take into account the probability of things being real, and then just weight them accordingly to with the probability of doing that. So the real complexity, for those wondering, if you want to consider an event and weight it by a P astro to say what's the probability of it being real, it's roughly equivalent to, you just have a P astro and you use that as a weight to multiply by, the probability for each individual event. So you take this as a weight in your sum when you're, in your product when you're multiplying everything together. So your probability of your parameters given, the data for that particular event is schematically you add this into weight. The complexity is that P astro itself depends on your model, right? So something could be, definitely real in one model where you predict there should be tons of signals with these values, but equally P astro could be 0 in another model where you predict there should never be a signal with these parameters. I mean, in reality, you're never actually going to get a P astro of 0 or 1. You're just going to get something very close to 1 or very close to 0. And if you, in effect, what you're saying is that, so let's say we had probability distribution for M1 in our short source distribution, M1 given lambda. Say it looks something like this with a mass gap. So we were never going to have anything in this mass gap. Okay, and we had an observation which was here. What in effect we're just saying is we had a noise fluctuation which took us from one side to the other into this gap. So it would be very unlikely to see this. But it's not impossible to get a noise fluctuation that big, so we just get a P astro that's very, very small. But the point is P astro depends on lambda. So when you're calculating the weightings depend on where you are. So that gets quite complicated, and you need to take this account into your alphas. So the way proposed is basically to pick a fiducial set of lambdas, calculate alpha from that, and do it perturbatively relative to that. And that's been proposed in these analyses to do this. I'm not sure from a formal mathematical point whether it's been rigorously proved that this is always going to work. That if you have a model which is sufficiently far away, you might need extra corrections to do this. But I've not thought of a better way to do it myself. So,
Actually, what are your sorry, please
Go ahead.
complete. Please go on.
So I was just going to say, coming back to your question, there are some papers which sketch out to do this. It's a bit more complicated. There's some subtleties. I'll add some links so you can go and read up about it. But yeah, I think there are still some open questions and research topics about how to make sure that this is robustly done.
But would you expect that it impacts the final estimation of hyperparameters? Would it greatly impact it? Or let me pose it in a different way. Since this analysis has already been done, has it impacted the estimation of hyperparameters in a big way?
The answer is no, it has not impacted parameters in a big way. And you can understand this basically by considering that the things that get weighted most in your product are the things with a P astro of approximately 1. So if you pick a sufficiently high threshold such that most of the events are likely to be 1, okay, you're basically just throwing away the least informative events. So throwing away something which doesn't add a lot of value doesn't change most of your results.
Okay.
So far, it's a big effect. I don't know that one is safe to assume in general that it won't have a big effect. I think in particular, for some assumed parameter distributions, it might be important because there's lots of weight in the low ends. But I think often it should be a reasonable approximation, even if it's not a perfect approximation.
Okay, sounds good. Thank you.
Excellent questions. So I know we're a few minutes past, but I did equally cover quite a bit of algebra, and there were quite a few complicated steps. So if anyone does have any more questions, I'm happy to stick around for a couple more minutes.
Hello.
And if you have time to go away and think of things and work through notes, you can drop them in Slack, and I'll try and pick those up later.
I have one question. About the selection effects, so the integration is over only the detectable events, right? So is it possible to compute it, the p det of theta from the events that have been detected till now, or one needs to do an injection study for that?
One really needs to do an injection study for this. You can't just rely on the detected signals, because the detected signals depend on both the detectability and also the astrophysical distribution of sources. So if you're not detecting anything at 300 solar masses, for example, if you're just looking at the detected events and the fact that none are detected there, you can't tell if that's because we can't detect 300 solar mass objects, or there are no 300 solar mass objects to detect. So you have to have a set of injections where you know what the true distribution is, so you can see what fraction of those are recovered.
Is only on the events that are detected, right? So will that make a difference, the things that we don't detect?
Yes, yeah. That's the whole point, that you need to know this threshold. So you need to understand what is the boundary between detectability and not detectable.
Okay, I see. Okay. And another question is like, what? So do we expect P at theta to change a lot from one observing run to another observing run?
Excellent question. We do expect it to change. How much it changes depends on a couple of factors. So it depends on the sensitivity of our detectors. So for example, as we get improved lower frequency sensitivity, we would expect P-det to increase for low mass systems, high mass systems, lower frequency systems. So that would change. It also depends on the data quality. So, you know, your threshold, what your statistic is where you can make a confident detection, depends on the data quality, depends how glitchy it is. So this threshold can potentially change run to run at a, you know, if you wanted a constant far, and if you wanted a constant P astro, it would vary run to run, because as the sensitivity improves, your true alarm rate goes up. So your, detection threshold would change because you're seeing more systems. So yeah, it does vary run to run. If you're just going at a constant, say, far threshold or something like that, it doesn't vary too much in terms of mass over the runs we've had so far. So you can potentially approximate that as constant. But to do things properly, yeah, you would need a different P-det to characterize the different ones.
Thank you.
Okay. Do we have any final questions for Christopher? I'm not seeing any hands up. So, okay, there's one more.
Sorry, so a follow-up question to what Sisti asked just now. So how would you combine this selection function from different runs when you're doing a combined study on estimating the population hyperparameters?
Yeah, so you can break up your inference to look at the individual runs one after another, or you could calculate a time-weighted P-det taking into account, the different periods of runs. Just because we don't generally care when something's detected, just that it was detected at once. So you can calculate, a P-det averaging over all the observing runs. The important thing is you add in the contributions from the different observing runs.
Okay.
Any more questions? Okay. So if not, we can conclude today's lecture. Thank you, Christopher.